Welcome to qnawire.
Okay, so we've got the following molecules. Actually, this one's a little different. Okay, and all we need to do is identify how many unique hydrogens we have, right? So, there's going to be 3 here, 3 here. Okay, are these sets of hydrogens meaningfully different, like in a chemical way? Well, no, because if we look at this carbon, right, it's not a stereocenter or anything like that, right? It's just a carbon that's saying, okay, here's a methyl group, here's a methyl group. We can rotate freely around this bond, and these methyl groups are indistinguishable from each other, which means that the hydrogens that are on these methyl groups that are indistinguishable from each other are going to be chemically equivalent, right? So for that reason, we can call these hydrogens 1, okay? They're chemically equivalent. Okay. And then for the remainder of the hydrogens on the molecule, remember there'll be 1 here, there's 2 here, there's 2 here, 2 here, and 3 here. Okay. This is the only carbon that's attached to 2 methyl groups and the rest of the chain, right? So the carbon here is unique, which means the hydrogen here is unique. Okay. This is the only carbon that's attached to 2 hydrogens, an ethyl group on one side and an isopropyl on one side. So this carbon is unique, which means these hydrogens are unique. This carbon is the only carbon that's attached to a methyl group on one side and then like a sec-butyl on the other side, right? Which means this is unique, right? We can tell these 2 carbons apart, so the hydrogens on them must also be able to be told apart, okay? And then finally, this is the only methyl group which neighbors a carbon that has a sec-butyl group on it. See how, like, even though these hydrogens are on a methyl group, they're not the same methyl group, right? This methyl group is the same as this methyl group because they're both coming from the same carbon, but this methyl group is not bonded to the same carbon that the other 2 are. So these hydrogens are unique. Okay, so we can continue to play this game with the following molecules, right? Again, we have a methyl group and a methyl group. Are they equivalent? Well, in this case, no, right? Whereas before we said we could freely rotate about this bond and we wouldn't be able to tell them apart. That's not the case when we have a double bond, right? What I mean by that is that these hydrogens are trans across the double bond to an ethyl group. These hydrogens are cis across a bond to an ethyl group, or we could say that they're trans to a hydrogen. Okay. Point being that they are chemically distinct. We can tell them apart. These are the ones that are on this side, and these are the ones that are on that side. And we can't just rotate about a double bond to swap them, right? You can't rotate about double bonds like that, but you can rotate about single bonds. Point being that the hydrogens here are distinct from the hydrogens here. And yes, there are 3 of them. I'm just drawing in one of them for simplicity. Now, this carbon has 4 bonds, meaning there's no hydrogens here, right? We can't see any hydrogens. It's already got 1, 2, 3, 4 bonds, no implied hydrogens. We do have a hydrogen here, right? And it's pretty obvious that this is unlike any other hydrogen. It's our only hydrogen coming from a carbon. It's a double bond. And then we've got 2 hydrogens here, right? And they're fairly obviously different from any of the other hydrogens that we may see. Okay. Hopefully this is starting to make a little bit of sense. Okay, so we move on, and then our third molecule is basically exactly like our first molecule, except for now we have a chlorine here and a hydrogen here as well still. Point being that nothing has functionally changed, right? These two methyl groups are still identical. We can just rotate about that bond freely and wouldn't be able to tell them apart, right? So 1, 1. But nothing else has really changed, right? We still have one hydrogen here that's unlike any other. Still have one hydrogen here that's unlike any other. Still have one hydrogen now instead of two hydrogens that are unlike any other. Sorry, there's two hydrogens here, right? And we still have three hydrogens here that are unlike any other. So we still have 5 unique hydrogens. Okay, now we get to this last example. And this is where there's another trick that we have to introduce, and that is the trick of symmetry, right? So this carbon, there's 2 hydrogens on it. This carbon has a methyl group on one side, and then a carbon attached to a chlorine and an ethyl group on the other side. Well, this carbon also has a methyl group on one side and a carbon attached to a chlorine and an ethyl group on the other side, right? So these two sets of hydrogens, because this molecule is symmetric down the middle, are identical, right? And the same is true for the methyls on the end. Okay. We'll call that 2, call this 2. And then finally, there's one more hydrogen here. It's not like any other. There's no other carbons on a hydrogen, no other hydrogens on a carbon that are attached to a chlorine, for example. So that we can call that 3. Okay, so we have 5 unique carbons in our first example. We have 5 unique carbons in our second example, 5 unique carbons in our third example, and 3 in our fourth example.